right. Another very important package in the tidyverse is dplyr. And dplyr allows us to do a lot of data manipulation tasks. And I would say this is probably, in my opinion, perhaps the single most important package in the tidyverse. This and ggplot2. I mean, all of the tidyverse depends on a bunch of the things, but this might be the single most important package in the tidyverse, perhaps in base R as well. I mean, granted, all of the operations I'm going to show you in dplyr can be done in other ways in R. It's in base R it can all be done. You can use apply and tapply and all sorts of things, but I find dplyr, the syntax and the language very useful, and so this, I guess, my personal opinion, one of the most important packages. Okay, you can load up dplyr by calling library dplyr or library tidyverse, and the idea behind dplyr is that it gives you kind of a limited number of verbs. Okay, it says it constrains your options and it helps you to think about data manipulation as kind of linking together certain basic operations. Okay, it says when working with data, you must figure out what you want to do, describe those tasks in the form of a computer program, and execute the program. And dplyr makes these steps fast and easy. So the important verbs, there's more verbs than this in dplyr, but I would say the important ones within dplyr are select, which we use to pick our variables, basically select columns. Filter picks the cases, which is used for rows. So select for columns, filter for rows. That's going to be the important thing for you to remember. Select the columns, filter the rows. Mutate creates new columns or new variables. Arrange changes the ordering of the rows. And summarize calculates summary statistics. It reduces the multiple values down into a single value, like calculating the mean of a set of numbers takes multiple values, boils it down to a single summary value, the mean. All of these are also paired with another variable or verb called group by. And you can form groups, and it's going to calculate or do these operations for different groupings in your data frame. Okay, but let's talk about some of the select and filter verbs, and that's what we're going to do. This is there's a cheat sheet available, very handy. I recommend you download it. Let's take a look at some examples here. So we're going to work through this Star Wars data set. Okay, this data set was created after the 7th movie, before the 8th and 9th movie. So there are 9 movies in the Skywalker saga. This data frame was created between the 7th and 8th movies, and so it includes information about different characters. Okay, so we have the name of the character, some physical attributes, their height, their mass, information about their hair color, skin color, their eye color, their birth year, which is measured in I guess years before the Battle of Yavin, which I guess is a canon event, happened at the end of the first, I guess, episode 4, where the Death Star blows up. That is the Battle of Yavin, and I guess Luke Skywalker was 19 when that happened because he was born 19 years before the Battle of Yavin. Anyway, sex, their gender, other things, their homeworld, their species, the films that they appear in, along with the vehicles that they've used in any starships that they've commanded. Okay, so we have that kind of information. All right, we can so here as an example, we can select columns using select. So here I'm going to say select from the Star Wars data frame or tibble, select the columns name, homeworld, species, and films. And so we select those columns, name, homeworld, species, films. Luke Skywalker is a human from Tatooine. C-3PO is a droid from Tatooine. R2-D2 is a droid from Naboo, so on and so forth. The films, within films, we have a vector of, I guess, if we select this, it would be a vector of the 5 films that Luke Skywalker had appeared in. We have an operator called the pipe. Okay, the pipe operator is % greater than %, and what it does is it takes whatever value you have in front of the pipe and inserts it into the function as the first argument into the function that comes after the pipe. So if you have x pipe f of y, that is equivalent to writing f of x comma y. Okay, so we're basically piping the x into the first argument of f. So the previous slide had select from Star Wars, name homeworld species films. This can also be written as take Star Wars, pipe into select, and select name homeworld species films. And I'm going to be using this pipe syntax because you can chain pipes. So the result of calling Star Wars and then select gives me this tibble. I can then pipe this tibble into another operation which will then kind of work with this result. And so it kind of does a step-by-step, first do this, take that result, and then do this, take that result, and then do this. Okay? And so so that's a nice way to kind of write our commands using pipes. The base R liked the idea of the pipe that was introduced in the tidyverse so much that they implemented the native pipe. The native pipe is found by taking a vertical bar and doing the greater than sign. The functionality of the native pipe is almost identical to the pipe that's part of the tidyverse. You can find a little bit more information about that at this link here. So you can do that. R, I believe, will insert the pipe kind of automatically using a shortcut keyboard shortcut. Command-Shift-M or Control-Shift-M will insert the pipe, so you don't have to constantly be typing % greater than %, but you can just hit Control-Shift-M and it will insert the pipe for you. All right, so as far as select goes, you can also put a negative sign in front of columns you don't want. So here I can say from Star Wars, select the columns other than name, eye color, and birth year. And so it drops those column names, and this is what we have. I can then pipe that result and just say head 3, and it will only give me just the first 3 rows of that resulting table. Here's another example of select where I can kind of specify a range. I can say from name through eye color. So kind of, traditionally with the colon operator, we give it integer values and we create a range of integers. But here we can also kind of use it with column names, and I can say I just want these columns name through eye color, and it selects height, mass, hair color, skin color, eye color. We also have some selector functions, helper functions. So we have things like contains, starts with, ends with, matches, everything, numeric range. You can also just ask for help on the select helpers in the tidy select. And so contains will basically, you put in a string and it will select any column that contains that string. You can starts with will be columns that start with a particular character string or ends with a particular character string. If you want to use regular expressions, you can select the column names that match a regular expression. Everything will select all the columns. Numeric range, sometimes you have columns named like x1, x2, x3, x4, and you can select the columns that fit some kind of pattern there. All right, so here's a few examples. I can say from Star Wars, select all the columns that ends with color along with name. Okay, so we got name, and then we get hair color, skin color, eye color. Here is a regular expression, a very simple regular expression. It says matches $. This just means it's going to end with the character S, okay? And so we get select name, but also mass and species, films, vehicles, starships, because these are the columns that end with the character S or match this regular expression. sometimes you're in a situation where you build a vector of the names you want to select. Okay, so it seems so sometimes you want to select these columns, name, mass, and height, and those column names, or the names that you want to select, are stored in this vector vars. Okay, so if you wanted to select those, you can't just do Star Wars select and you put in vars. Okay, because then dplyr is going to look for a column called vars and it's going to say I couldn't find it. But what you do is you throw vars into the function all of or any of, okay, and it will select the columns. It will look at this vector, turn those into basically understand that these are column names that you want to select, and it will select those column names. So here we select name, mass, and height. Filter is used to filter down your rows. You specify rows using filter. Select is for selecting columns. Filter is for specifying the rows. As far as the filtering your rows, basically you give it some kind of logical vector, okay, and it will return the rows for which that logical vector is true. So here I'm going to say Star Wars filter, and I give it the logical vector name equals R2D2. Basically, that name column is compared to R2D2. It's going to be false anytime the name is not R2D2. It's true only when it is R2D2, and therefore it returns only that one row where the name is equal to R2D2. Certainly there's many other things. So for example, you can apply multiple conditions, and that's equivalent to using an AND. So here I have this condition. This is going to be a true-false vector, a logical vector, where we're going to say species is in human or droid. Okay? Now it's important that you do not use species equals human comma droid, because if you did species equals human comma droid, what that will do is it will take that vector human comma droid and it will recycle it. So first row it will be human, second row droid, third row human, fourth row droid, and then human, droid, and then you will only get a match if you have human in an even row or droid in an odd row. Okay, and if you have a human in an human in an odd row or droid in an even row, if you have something kind of the other way, right, then it won't match. So if you want to kind of say species is basically one of human or droid, then you use %in%, and that will select basically where the species is either human or droid, regardless of its row position. You can also specify height less than 175 or some other condition. This is a logical condition, and it will impose that limitation here. Filter is very powerful when you pair them with regular expressions. I haven't taught you regular expressions yet, but there is a function called string detect. This will return a logical vector of true or false value, and so you can say filter, and here I pick name, and this means begins with F. So I'm going to say detect this regular expression, and if it detects that regular expression as true or false, if it does, it will return true, and so we're going to filter down to the rows where it begins with the character capital F, and we get these two rows. We have Finn is somebody, I don't know who that is, and Finn, I believe, is from the seventh movie, I guess the later trilogy movies 7, 8, and 9, and so we have that. Okay, we have so the dplyr functions work well with the pipe. Okay. You can also use OR, the vertical OR operator, to kind of get vectorized or operators. So we can say Star Wars, I want hair color to be none, or eye color to be black, to select our to filter our rows. And then after that, I just want to select the columns, name, species, homeworld, hair color, and eye color. And so here I get Darth Vader, who has hair color none, eye color is yellow. We have Greedo, hair color is missing, eye color is black. IG-88, hair color none, so on and so forth, and we get these characters from the movie. Once you have characters, or once you have things done, you might want to arrange your results, arrange the rows. And so here I'm going to say from Star Wars, basically I'm not filtering any of the rows, but I'm going to just select these columns, name, birth year, height, and mass. And with those results, I want to arrange in descending order by birth year, and then break any kind of ties based on mass. So the oldest character in this data set is Yoda, born 896 years before the Battle of Yavin. Then we have Jabba the Hutt, I guess 600 years before then. Chewbacca, born 200 years, etc., etc. We have a tie between these two characters, Ki-Adi-Mundi and Qui-Gon Jinn. And so that tie is broken by mass, because mass is specified without the descending modifier. Its smaller values get ranked before others. So Ki-Adi-Mundi with a mass of 82 comes before Qui-Gon Jinn with a mass of 89. I guess that other character with a capital F was Finis Venelorum, but I don't know who that is. Another operator is slice. This is just kind of, you can select rows based on their position. So you can say I want rows 5 through 10, and so we get those 6 rows, and then basically it renumbers them from 2 rows 1 through 6. Slice sample will select rows at random. Okay, so a lot of times, so you might wonder, like, why would I want to select rows at random? Well, sometimes you need to do some random sampling, and it's useful in that case. But sometimes you just kind of want to check to see if your calculations are going well, or how they're working, and things like that. And so a lot of times you just kind of want to take a look at the data frame after you've performed some kind of operation. Oftentimes, to take a peek at the data frame, we might use head. Okay, so after doing some operation, I might do like head of the data frame, and that will give me the first 6, 10, however many rows I want. However, sometimes we're in a situation where the operation you want works successfully for the first few rows, because maybe there's a certain condition that applies to the first few rows, but then later on that the operation was no longer successful. And if you only use head, you only get the top few rows, and you might not detect that something went wrong. So by doing slice sample, you're going to get a random selection of rows, and that will give you a better sense of whether your operation was successful across the data set, okay, across the multiple rows. It's not a guarantee. So you could do slice sample n equals 100. You get a random selection of 100 rows, and you might not detect any problem, but it's possible that problems still do exist, and you just don't detect them. But slice sample might give you a better sense of kind of what your data frame looks like, and not just the top few rows when you use head. You can also do slice min and slice max. This is kind of like doing arrange and then slice, okay, or and then head. So for example, slice max mass n equals 3, it's going to basically select the 3 individuals with the highest mass, okay? Slice min would select the individuals with the lowest mass, and so on and so forth. So it's kind of like taking a range to put them in order, and then selecting the top few rows. So it's just a little shortcut, not critical. You can do this yourself without the thing, but it's handy to have. Mutate. Mutate will create new variables. So, for example, we can take the column height, and perhaps, which is currently reported in centimeters, and perhaps I want to report it in inches. So I would take the column height and divide by 2.54, and it calculates that. Now, one issue is that when you create a new column, it always puts that column in the last position, the rightmost position. And so in this case, because the way tables work, it doesn't print any columns beyond what is visible on the screen. So height in inches, just doesn't appear on my thing. So here I'm going to mutate, and then I'm going to select just the columns, name, height, and height in inches, and then I'm going to select that top row. And so we see Luke Skywalker is 67.7 inches, around 5'8". Now, when you use mutate, it is important that the number of values produced by mutate, this new variable that you are creating, because it's creating a new column, it needs to have the same number of rows as the data frame, okay? So if I used something like mean with mutate, it's going to end up just kind of taking the mean value and then just duplicating it across a whole bunch of rows, which is probably not what I want to do. Cumulative mean is kind of a silly operation when we're dealing with the mass of characters. Cumulative mean, any of these cumulative functions work best with time series operations, and it's kind of like over time, this is the running mean. But cumulative mean would be kind of like, what is the mean of the values we've seen so far? So we begin with 77. After we see 75, our mean so far is 76. After we see 32, the mean of the three characters drops down to 61.3. After we see 136, then it bumps up to 80. And so that's what we get with cumulative mean. Again, doesn't really make sense to apply in this data set. Works much better with kind of a time series, and you'll say, on the first day it was here, and then as we saw more and more values, the overall mean is approaching this perhaps asymptotic value or something. Values that are useful for mutate, or functions that are useful for mutate, we have pmin, pmax, element-wise min and max, cumulative min, cumulative max, cumulative sum, cumulative product, between, which will return a true-false value, cumulative mean, okay. We also have lead and lag, and then you can do n-tile, which will basically bin the values into n different buckets, and then you can use it as some kind of categorical variable. I'm going to show you some examples of these functions. Again, doesn't quite make sense to use on this particular data set, but you'll just kind of get a sense of how this works. So the original data, I'm just going to look at the name, the mass, and the birth year. And then we're going to mutate these additional variables, and they, again, anytime you create new variables, they just kind of get tagged on. So cumulative minimum mass is basically, of the values we've seen so far, which one is the lowest value we've seen. So we start off with 77, so that so far is the smallest value we've seen. Then we see encounter 75, so that takes the new champion spot of smallest value, 75. Then we see R2D2, which is even smaller at 32. Then we see 136, which is not lower than 32. And none of these other values are lower than 32, so our the minimum mass that we've seen so far remains 32. If later on we encounter a value like 31 or 29 or 7 or whatever, then that will become the new cumulative minimum mass. Okay, again, cumulative functions generally make most sense for time series things. The ratio, you can kind of just do a calculation here. I'm doing mass divided by the mean of mass, okay? So here I would calculate the mean of mass, which is going to be the same for everybody. I'm going to do na.rm equals true so that we don't, if somebody's mass is an na, we're not going to get an na. And so, whatever the average mass is, which I think is just under 100 kilograms, then, Darth Vader of 136 is, 1.4 times the average mass. Luke Skywalker with a mass of 77 is, 0.791 times the average mass or something like that. Okay. P min is element-wise minimum. Doesn't really make sense to do this, but we're going to do between the mass and the birth year, which one is smaller? So between 77 and 19, element-wise, which one's smaller than 19? Between 75 and 112, which one's smaller? 75. Between 32 and 33, which one's smaller? 32. Between 136 and 41.9, which one's smaller? 41.9. So that's P-min, and you have P-max as well. And then lag, all that does is it just takes one of the columns. Here I'm going to take mass year P-min, and it will offset it by 2. So it will just lag those values by 2. The opposite of lag is lead, and so then it would shift values up. So that's what you get. Okay, so those are just some examples of things you can do with mutate, and I showed you examples of select and filter, and these are some of the basic and important functions within dplyr.